Hi all, good evening and welcome to the class. For those who didn't join last Tuesday's live lecture, so I am Prakriti. So I'll be handling these live sessions every Tuesday for you, for the course Essentials of Data Science with R software. So yeah, the last class we just saw some theory about statistics and data science and why it's important and what you will be learning in this course. So yeah, so in week two's lectures, uh, Professor Shalap has talked about probability theory. So probability is also like one of the mathematical methods that you apply in data science. So yeah, week two's lecture is more like an introduction, theoretical introduction to probability theory. And from next week onwards, we'll go more detail into the maths of it. And we will be solving a lot of numerical problems and uh, we'll be practicing with R. Since a lot of you people have been asking me to solve numerical problems. Yeah, so last week we just like had a session about how to get started with R. So even in today's class, it'll be more of a theory. It'll just introduce you to a lot of topics in probability. So from next class, yeah, there'll be some problem solving. Although today we'll just look at some assignment questions, where you won't be numerically solving anything, but yeah, it's just to make you understand the terms in probability. So yeah, let's get started with, I hope I'm audible. Yeah. So yeah, we'll start with probability theory. So if you try to analyze your everyday activities, at every moment you're trying to compute a probability in your head and you're trying to create a probability model in your head. So why are you trying to create a probability model? So for example, like even for the simplest scenarios, like uh, whether it's gonna rain, is it gonna rain or not tomorrow or today? Like, is it gonna rain? So how do you know if it's gonna rain? So if the sky looks cloudy, you just think that, oh, there's probably like 60% chance for it to rain. So if the sky is clear and has been cleared for the last few days, you might think, oh, there's no chance for it to rain. So yeah, this is just an example of how like probability comes into play in your daily activities, like without you even knowing how you have constructed that probability in your head. So in this lecture, we're going to talk about different small topics. And yeah, I request all of you to mute yourselves unless you have questions. Sorry, that's a Mansi. Mansi, were you saying something? All right, yeah. If you have any questions, you can just unmute and or raise your hands and just start talking. So yeah, we'll talk about different topics related to probability theory and we'll try to interconnect them. And then we'll also talk about some maths and we'll try to connect maths to the real application and with computation. So yeah, let's start. So yeah, in last week's lectures, you would have learned about statistics. So statistics is basically the science of learning from data. So like if you want to learn and know about anything, so you must first collect data and then you have to learn from the data. So statistics helps you do that. So it is related to the collection of data and then extracting the hidden information by using descriptive statistics and coming to conclusions. So sometimes statistical analysis begins with a given set of data. And this kind of statistics, it describes, summarizes, and analyzes the data. But in case there's no data available, so what do you do in such cases? So you try to design an experiment to generate the data appropriately. So at the end of that experiment you design, the data is described and summarized using tools of descriptive statistics. Like for example, like scientists developed vaccine for COVID. So like before the pandemic, nobody had information, nobody had data about what vaccines would be effective. So how did they generate that data? So they designed experiments, probably like mouse models. So they might have like created the vaccine, they might have synthesized the vaccine and then injected the mice with vaccines. And then they would have exposed the mouse to the coronavirus. And then they would have observed if the mouse gets COVID after being vaccinated, or does it not get COVID? Is it immune against the virus? So yeah, based on the experiment, they collect data and then they come to a conclusion whether the vaccine is effective or not. So that's what you call like this kind of statistical method. So whatever we are going to understand, there'll always be a chance that we may be wrong. So whenever we're trying to use the tools of inferential statistics, the concept of chance is considered and utilized to draw a conclusion from the data. So we always say that there are chances for this to happen and that to happen, but it might be long. Like we said with the cloud example, the clouds are gray, then you might be inferring that, oh, there might be rain. The chances of rain are very high. But yeah, that might be wrong as well. So like a careful description and presentation of the data helps us in inferring an appropriate probability model for any given set of data. So once we have created the data, we need to be sure that the model is correct. So what do? We try to, again, the same thing. So this is just like briefing you again about what is statistics. You generate the data, you use statistical tools to extract the hidden information to come to conclusions. So because at every step, you're trying to judge whether the probability model is correct on the basis of probability and whether you're going to give a correct statistical inference or not. So like, for example, if I ask in your class, what is the average age of all your classmates? You can say something like 22 years or 23 years. So this doesn't mean that everybody's age in the class is 22. They may be like 21 years and 5 months. They might be 22 years and 1 month and so on. But what you do, you already like create a model in your head. You just like try to calculate the mean age of everybody in your class, and you just say, oh, the average age is like 22. So that's a correct model. So if somebody says, oh, the average age of my classmates is 70, that would be wrong. So yeah, all your conclusions, they're based on some probability models like these. So now what are the different elements of probability? So probability of an event is subjected to various meanings and interpretations depending on how somebody says it or how they want to use that information. For example, like if a doctor says that there's 70% chances that a patient will be cured, what does this tell us? So it mostly gives the impression that the patient will be cured. But if somebody says something like Dr. B, the like he's not good enough, only 5% patients survive. So that's not a very reliable doctor to go to. So yeah, all these like statistics in the life that you see, they help you decide your actions. So basically, when we talk about the interpretations of probability, there are two types of interpretations. So one interpretation can be based on the frequency of a particular event to occur. And the another type of interpretation can be subjective interpretation. So what do these terms mean? So let's look at that now. So the first one was frequency interpretation of probability. So the probability of a given outcome of an experiment indicates the property of the outcome. So yeah, if somebody says like the doctor, like he's so good, there's 90% chances that your disease will be cured. It means that the doctor is a good doctor, and the way he does his surgeries, they follow the correct procedure, and yeah, it's effective. So the outcome of the experiment indicates a property of the outcome. So such a property can be determined by continual repetition of the experiment. A popular interpretation of probability is as follows. The probability of the outcome is observed as the proportion of the experiments that result in the outcome. Like, again, let's just take this doctor example. So throughout his career, if the doctor has just cured 2 patients, one patient has died, but the other is cured. So with this frequency of his treatment, you cannot decide to any conclusion. You can't say, oh, is the doctor good? You can't say if the doctor is bad. It could be just because the patient who died, he was like really very sick. There was nothing that could be done to cure him. So just based on two observations, you can't decide to a conclusion. So, but let's take another case where the doctor has treated 1,000 patients. 95 patients, sorry, 995 patients have survived, but just 5 patients have died. So with this frequency, like you could confidently say that, oh yes, so the treatment is effective. So yeah, again, your interpretations depends on the frequencies of the observation. So that is what you mean by frequency interpretation of probability. Now the next one is subjective interpretation of the probability. So now in case, if you try to consider the subjective interpretations of probability, so in this case, the probability of an outcome is not thought of being the property of the outcome. It is just considered as a statement about the belief, like personal belief of the person who is quoting the probability. So the probability is about the chances of occurrence of the outcome based on a person's belief. So let's take a simple example. Let's say I am meeting with my friends. So we are meeting with my friends. Like one of the friends, she always comes 15 minutes late. And another friend always comes on time. And another friend, she always comes early. So I can confidently say that two friends will be there on time when I reach the place. But I can also say that the other friend who always reaches 15 minutes late, this time also she'll be 15 minutes late. But there's one more friend, like sometimes she's on time, sometimes she's late. So like 50-50 chances that she's on time and she's late. So when I ask my other friends if they think the other friend, she will be there or not. Some people might think, oh, she'll be there on time, but I might think she'll be late. Although like the chances are 50-50. So in this case, it's just a subjective interpretation. It's just like what the person at that moment thinks the outcome will be. So yeah, so my interpretation is that she will be late, but another friend's interpretation is that she'll be on time. So it's subjective. So this is what you call subjective interpretation of probability. So this is what yeah, like you said, it's just expressing one's degree of belief. And yeah, interpretation of probability is often favored by decision makers. Like somebody is who has like if let's say like in decision making, we only rely on such statements from somebody who is uh, who's a pro in that field, like somebody who has all the knowledge in a particular field. We can rely on their subjective interpretation. So now when we come to these aspects of probability, like irrespective of the frequency or the subjective interpretation, so practically there's a maths behind these. So the mathematics behind all these, they are generally usually the same. So like, yeah, again, the cloud example, like let's say the probability of raining tomorrow is 0.8. So there's a math that 80% chances there will rain. So the maths might have been because of data, which is like the frequency, because like I have lived in that city for so long. So in 100 days, like in 100 cloudy days, in 80% of those days, if the clouds look like that, it's gonna rain. So here there's a frequency aspect as well, and there's a subjective interpretation as well. So in both these cases, yeah, so there's always a maths behind it. So now we've just learned about how to interpret probability, and now we'll just learn about each of the elements. So sample spaces and events. Just mute. Yeah. So first of all, there's an experiment, like we said. So any activity for which the outcome is uncertain can be thought of as an experiment. So we call it an experiment because until the event happens, we don't know what the outcome is. So like just for example, the usual example that we use in probability. So we toss a coin. So tossing a coin itself is an experiment because we don't know if the outcome is going to be a head or a tail until we toss a coin and we see the results. Similar is like drawing cards. Until we draw the card from the deck and look at it, we don't know what card it is. So that's why you call it an experiment, because the outcome is uncertain until you do it. And the uncertainty concerns in the sense that the outcome of the experiment is not known till the experiment is completed. So the outcome is not predictable with certainty in advance. Although you can just say like there's this much chances that the outcome is possible. So that's the whole thing of probability. So now what's sample space? So we saw about experiment, and one other thing is sample space and another thing is event. So the outcome of the experiment is not known in advance, but we know what are all the possible outcomes. So while tossing a coin, we know that the possible outcomes are head and tail. So these are the two possible outcomes. So this is the sample space. And while drawing cards, we know what the possible outcomes are. We know the cards could be ranging from numbers 1 to 10, J, King, like Jack, King, Queen, and Ace. So we know that it could be either of these, and it could be any of the colors. It could be red or black, and it can have any of the four shapes: diamond, heart, club, and what's the other one? Spade. Yeah. So we know all these. So we know that uh, the outcome is any of these. So all of these outcomes that are possible is called the sample space. But the subset of the sample space is known as the event. So there can be all these many possible outcomes, but you draw cards. I draw 4 cards, like 1 heart, 2 spade, 3 heart again, and 4 clover. So this is now the event. So that is a subset of your sample space. So these are the major terminologies that you'll often come across. Sample space is the all possible outcomes. Event is a subset of that. So the outcome of the experiment is E. Then we say that E, the event has occurred. So, sorry. Sample space is denoted by capital omega. So event is denoted by E. So again, here that's just an example. So if the outcome of an experiment consists in the determination of the gender of a baby, so what is the sample space? The baby is biologically born either as a male or a female. So this is your sample space, capital omega. So M is male, F is female. But when it could be either just one of these, unless you have twins. So there's just one child being born. It can be either male or female. So we know that outcome after the child is born. So now the event is M. So it's a male child that is born. So that is an event. So this is just a simple example. And there's also similarly, there's another example. So let's say there are 3 students who have got 3 positions in the game. So if 3 students have to get 3 positions in a game, like first, second, and third position, then the experiment consists, the sample space would be all possible orders of these. Like student number 1 can come first place or second or third. And same, student 2 can come first, second, or third. 3 also can come first, second, third. So by order, I mean, so if the outcome is 2, 3, 1, it means that, sorry, the outcome 2, 3, 1 means student 1. Yeah, so outcome, this means that the first student gets second place, the second student gets the third place, and the third student is the first place. So this is one order. So another possible order could be first student comes third, second student comes second, third student comes first. So it can be any of these order. So now the sample space is all possible orders of 1, 2, 3, and the event is any of these orders. So this is a subset of this. Again, so another example is just an experiment conducted to know the dosage of a medicine. So the dosage is increased continuously till the patient reacts positively. So one possible sample space for experiment is for omega to have all kinds of positive numbers. So the dosage can't be negative. You can't like introduce some negative dosage. It has to be no dosage, which is 0, or it has to be greater than 0. So any possible number is drawn like this. So this is one more example. And we'll look at more symbols and some notations. So we have understood the concept, but now to integrate them mathematically, so these are some terms that are used. So the outcome of a random experiment is called a simple event or elementary event, and denoted by small omega. So this is your sample space. Each element is like omega 1, 2, 3 till k, all possible outcomes. And the subsets of events are called they're denoted by capital letters. So one event can be A, which is just like omega 1 and omega 2 happening. And B can be just omega 10 happening. C can be omega 5, 11, 15. So these are all events that are denoted by capital letters. Also, like set of all simple events that are contained in A is like denoted by omega A. And the event A bar with like a horizontal line on top, it refers to non-occurring of A and is called a complementary event, which is opposite to A. So like simple example, we have numbers 1 to 10. So A is the set of all even numbers. So what is the complementary of this? So the complementary of this A would be the set of all odd numbers. It's just the opposite to that. So since the outcome contains all, this event contains this, since this omega, the sample space, contains all possible outcomes, we say that omega will always occur and it's called a sure event or certain event. We know that if we do that, any of that is always going to be there. So it's sure that there's a possibility of any of those elements to happen. So on the other hand, if we consider a null set as an event, then it means that this event can never occur. It's called an impossible event. It's just denoted by an empty set, and it's called like null set denoted by 5. And so the sure event is the set of all elementary events, and the impossible event is an empty set with no elements, no elementary elements. And let's look at this with examples. So if a die is rolled once, so then the possible outcomes are so the die has 6 faces. So the possible outcomes can be number of dots 1 to 6. So it can be 1, 2, 3, 4, 5, or 6. So let's consider an event A where an even number of dots on the upper surface of the dice. So this is so the event is like 2, 4, and 6. And A complementary again is the odd numbers 1, 3, and 5, like I just said before. Now again, just coming back to the definitions, elementary event is an event defined to observe only one particular number. So like whatever is in the sample space, we know that it will happen for sure. So that is an elementary event. So sure event is the event that a number, so let's say like we roll the dice. A sure event is when you say that you get a number that is greater than or equal to 1. So it is so obviously you'll get numbers 1 to 6. So an impossible event here in this case would be getting the number 7 when you roll a dice. So that is not going to happen because there's only numbers 1 to 6. So that's impossible event. Now let's say you throw 2 dice simultaneously. So what can happen? You can get number 1 on one dice, number 1 on the other, or any other number on the other die. So like based on that, you have like 36 different events. So like 1, 1 on both dice, 1, 2, and 6, 6, and so on. 36 possible events, which are these. Like when you roll 2 dice, these are all the possible outcomes. So now let's define event A as upper faces of both the dice contain the same number of dots. So what does this mean? Both the dice should show the same number. So in this case, the sample space is 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So another event B, omega B, is defined as sum of all, the sum of numbers on the upper faces is 6. So it means that you add up the dots, it becomes 6. So it can be either one dice can have 1 and the other can have 5. So 5 plus 1, 6. So it can be 1, 5, 2, 4, 3, 3, 4, 2, or 5, 1. So this is the sample space in that case. So again, a sure event is getting either an even number or an odd number in the die. But an impossible event is the sum of two of the dice is 13. So that is impossible because the maximum number sum would be 6 plus 6, 12. So 13 is an impossible event. Now let's understand this set theory and understand these probability events using Venn diagrams, which is a concept of set theory. So Venn diagrams are just like you represent them using circles. So one event, like one sample space is one circle and another experiment sample space is another circle. So one event is one circle. So suppose A and B are two events of a sample space omega. So we define a new event, which is A union B. So this is one thing, A union B. So A union B is called the union of events A and B. So A union B means it contains all the outcomes that are in A and B, also the outcomes that are common between A and B. And the next one is A intersection B. A intersection B means that it's an intersection of the events A and B. It consists of all the outcomes that are shared between A and B. So it has to be in A, it has to be in B also. So if event A intersection B will occur, it means A and B also will occur. So yeah, this just tells you what a Venn diagram is. Let's look at that. So this is a Venn. So this square, this rectangle is a sample space. A and B are events. So A union B. So this shaded portion, it shows A union B. So all the elements in A and all the elements in B and also the common elements between A and B. So from a statistical person, it's like a perspective, it's the elements either in A or B. So it's just all the things combined. And this is a representation of A intersection B. Only the things that are common between A and B, which is represented by this shaded area. So the intersection of events A intersection B in the set of all simple events A and B, which occurs when the simple events of A and B occur. So like mathematically, it's and A and B. So while A union B is A or B, and A intersection B is A and B. And this is A minus B. It means that the elements that are in A, but they are not in B, as you can see in the shaded area. So it can also be represented as A intersection B complement. So what is B complement? B complement would be everything outside the circle. Like this whole area will be shaded gray. So that is B complement. And A is this whole A is shaded. So what is common between B complement and A? This part is the common part. So it's also A minus B is also represented as A intersection B complement. And similarly, B minus A is B intersection A complement. And then, so this is what A complement means. So this is A. So anything that does not belong to A is A complement, as you can see here. And here is a subset. So let's say here A is a subset of B. It's like this. So all the elements in A are also present in B, but all the elements in B are not found in A. So yeah, so A is a subset of B here. And another term is disjoint events with set theory. So two events A and B are disjoint if A intersection B is a null set. So there's nothing common between A and B. So that is called a disjoint set. So like both events cannot occur simultaneously. So it's like A and A complement are disjoint events. Like what is here is not here, and what is here is not here. So there's nothing common between these two. And so that is an empty set. So these are disjoint events. So there can be mutually disjoint events. Like just an example, like event A is this set of all even numbers in the like dice, which are 2, 4, 6. And odd numbers are 1, 3, and 5. So these are mutually exclusive. So there's nothing common between these two. And then like you can also like consider a union between more than two sets. It's not just like it has to be A union B. There can be multiple events, and you can also like calculate A union B union C union D and so on. And similar with intersection. You can also have intersection for multiple events. A intersection B intersection C intersection D. So this is set theory. Then now let's move on to the relative frequency and probability. So yeah, there is a relationship between relative frequency and probability as well. Let's just see how it is explained and derived. So like I said, there's a close connection between relative frequency and the probability of an event. So a random experiment is described by the possible outcomes. For example, getting a number between 1 and 6 when you roll a die. So suppose an experiment has m possible events. When the experiment is repeated n number of times.
देखो
I'm sorry, I just had to unmute somebody. So you can repeat this dice experiment multiple times. So let's say like one event can be described as you roll the dice 5 times, and all the outcomes in that event is one set. And you can repeat this experiment like 10 times. So that is n denoted here. So what is relative frequency and probability now? So now we can count how many times each possible outcome has occurred. So I have conducted this dice rolling experiment for 10 times. And each time I roll the dice 5 times. So I can calculate what is the frequency of 1 to occur. What is the frequency of 2, 3, 4, 5, and 6 to occur? So how do I do that? So let's say in 10 dice rolls, like 10 times I roll the dice, I got 1 twice. So 2 is the absolute frequency for 1 to occur. So 2 is absolute frequency. Now what is relative frequency? So what was the total? I roll the dice 10 times. So that is the total number of the events. But the absolute frequency for 1 was 2. So the relative frequency of 1 is 2 divided by 10. So that is what this formula tells you. The relative frequency of a random event A with n repetitions of the experiment is calculated as n1, the absolute frequency of the event, ni, the absolute frequency of I to happen, divided by total number of occurrences, like total number of dice rolls. Like for example, like the same thing I said, like let A of I be the event where I get 1. So let's say A1. So the frequency of A1 is, relative frequency of A1 is 2 divided by 10. So which is 1 divided by 5. So now let's connect relative frequency and probability. So if you assume that the experiment is repeated a large number of times, so mathematically it means that this n would tend to infinity. But when you do all this, the experimental conditions remain the same over all the repetitions. So the relative frequency converges to a limiting value for A. So the probability of an event A to occur is the converged limiting value for the relative frequency of A to occur. So let's just take an example so that you can understand what I mean by limiting frequency, like uh, limiting what is this? Yeah, limiting factor of the frequency A. So suppose a fair coin is tossed 10 times. What do you mean fair coin? So fair coins means that the coin is of proper shape. It's not like tilted one side so that it favors head more than tail to occur. So fair coin is like both the sides of the coin are like uh, straight and with no bumps. So that's a fair coin. So a fair coin is tossed 10 times. So the number of heads observed is 3 and the number of tails observed is 7. So these are the absolute frequencies for head and tail. So now, like the probability of head and tail are equal. We know that the probability for head and tail to occur is 0.5. So how are we saying that? But in our observation, the probability for head is 0.3, the probability for tail is 0.7. This is just based on one experiment. But let's say we continue this experiment for so many times and we record this frequency, it will converge to 0.5. Like both the frequency of head will be 0.5, frequency of tail will also be 0.5 if you conduct the experiment for enough number of times. So that's what you mean by converging, like limiting value 0.5. So when the coin is tossed a large number of times and n tends to infinity, both frequency of head and frequency of tail will have a limiting value 0.5, which is the probability of getting a head or tail in tossing a fair coin. It's just the same thing represented. Let's go. Now, how do you do this with R? So this can easily be simulated with R. So it's very hard to manually calculate, like note down, like in this event, how many heads occurred, how many tails occurred. So, but R can do that easily. So you can just simulate. So let's say getting a head is 0 and getting a tail is 1. Let's just code it like that. Let's say we repeat the experiment 10 times. So what is this? So this is like random sampling, which we saw in the last class. So how do you do random sampling? You can do with replacement. Like because like when you toss a coin once, the outcome is head or tail. You note it down. When you repeat the experiment again, the outcome again can be a head. So that's called like random sampling by replacement. So this is how we do that. So the values are either 0 or 1 and you conduct the experiment 10 times and with replacement true. So maybe I'll just show you how to do it. Just give me a minute. Yeah, maybe I'll just show it later. I'm not able to show you both. So yeah, let's just say you do this random sampling for 10 events. So the outcome can be 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. So this will be your outcome. It could be anything. So now when you calculate the frequencies of this, So it could be like, so again, 7 times head, 3 times tail. So this is what you get when you do it 10 times. So we can try repeating the experiment for 100,000, 10,000 times and see what happens. So when you do it for 10 times, you get 0.7 head and 0.3 tail. Again, you're repeating for 10, you're getting the same thing. And now you're doing it for 100 times. Now you can see that the probability for, the frequency of head is 0.55, frequency of tail is 0.45. So you can see that compared to the last event, like lesser frequency. Yeah. So you can see that compared to like when you conduct the experiment 10 times, you can see when you do 100 times, the values are converging towards 0.5. So this is almost close to 0.5. Like 0 is also almost close to 0.5. 1 is also close to 0.5 here, like head and tail. Now you conduct the experiment for 1,000 times. So you can see that the frequency for head is 0.519 and tail is 0.481. So this is even closer to 0.5, 0.5. It's almost like 0.51 and 0.48. So yeah, when you do this with R, you get the same thing. So you can just see that like with the number of experiments increased, the frequency of head and tail is converging towards 0.5, which is the probability of head and probability of tail that you always use like when you calculate a numerical problem. So now let's look at another example with like a dice. So let's say a fair dice is rolled and its outcome is the number of points in the upper face. It could be either 1, 2, 3, 4, 5, 6. So we are repeating the experiment 100 times and we calculate relative frequencies. So let's say when we roll the dice 100 times, number 1 has occurred 15 times, 2 has occurred 10 times, 3, 25, 14, 6, like these many times. So the relative frequencies would be 15 by 100, 10 by 100, 25 by 100, and so on. So these are the relative frequencies for 100 times. Again, you do it with R. So you could see that the frequency for one, so like before that. So you always like like when you calculate numerical problems, we know that probability of head is like 1/2 and probability of tail is also 1/2. Similarly, in the dice experiment, the probability of 1 is 1/6. We use 1/6 and probability of 2 could be 1/6. So the 1/6 is 0.166 something. So yeah, we do the experiment for 100 times. We can see that the frequency of 1 is 0.1, 2 is 0.17, and yeah, the 4 is 0.2, and so on. Now we repeat for 1,000 times. It's almost like close. There's no 0.2. So everything is like in the range, like 0.14, 16, 18, 15. When you do it for 10,000 times, you could see that they're all very close to 0.166. Here, 1 is 0.16, 2 is also 0.16, 3 is also 0.6165. Yeah, so if you repeat it for more number of times, it'll all converge to the value of the probability that you use. And now the next thing is axiomatic definition of probability. So yeah, this is again the relative frequency slide. Oh, we already saw this. So yeah, so when you do an experiment, how do you know that you stop the experiment? How do you know that the value has converged? And how do you know that that is correct? So there are always a set of rules for how do you define the probability of an event. So that is called axiomatic approach for probability. And so, yeah, this is from a purely mathematical point of view. So we suppose that for each event A of an experiment with a sample space omega, there is a number denoted by probability of A. So this probability of A has to satisfy these three rules. So axiom 1 is every random event A has a probability within 0 to 1. So you have never seen a probability of 2. So it's always like 0 to 100. It's like 100. It can be 0% or 100%. So it can be 0 or 0.5, which is 50%, or 1, which is 100%. And then the sure event has a probability of 1. So if the event is definitely sure, it's 100% chances for it to occur. So the probability of a sure event is 1. And then for any sequence of disjoint or mutually exclusive events, so this would be the value. So A intersection A1 intersection A2 intersection A3 intersection till AN would be probability of A1 plus probability of A2 plus probability, like all summation of all these probabilities. So yeah, it will just be summation of all these probabilities, considering that all these events are disjoint or mutually exclusive. So these are 3 rules. So axiom 1 states that the probability that the outcome of the experiment is any number between 0 and 1. Axiom 2 states that with probability 1, the outcome will be a member of the sample space. And axiom 3 states that for any set of mutually exclusive events, the probability that at least one of these events occur, the intersection, is equal to the sum of all their respective probabilities. So this axiom 3 is called the theorem of additivity of disjoint events. So we'll later see that there's a theory of multiplication also, but this axiom 3 is called theorem of additivity of disjoint events. Yeah, this is just, yeah, so this was all about the lecture part, the theoretical part. So now let us just try to solve some questions from last year's assignments. Let me share that screen. Share this. Mm. So yeah, let's now just solve these questions one by one. Is my screen? Yeah. Yeah, so in a medical experiment, so there are 8 medicines, like 1, 2, 3, 4, 5, 6, 7, 8. So they are given to 8 patients. So the sample space of this experiment. So it could be that patient 1 is given medicine number 2. Patient 2 can be given medicine number 8. Patient 3 can be given medicine number 5. So this order can be anything. It's just a random order. So the answer to this question would be all orderings of 1, 2, 3, 4, 5, 6. Because okay, yeah, I can share the last year questions after we discuss it in the class, because the questions are very similar to your current assignments. It's just that you might have different values and like different statements. So yeah, once we discuss these in the um, live session, I can share these. So do you have access to the folders where the slides are shared? I'm not sure if the course coordinator gave you that. Can anybody just confirm? Okay, I will just put down. I'll check that later. So yeah, like I said, the order can be like patient 1 is given medicine number 1, patient 2 is given 2, 3, 4, 5, 6, 7, 8. It could be of this order. The event could be this order, or it can be 1, 3, 4, 5, 7, 8, 6, 2. So it could be any order of these. So the answer is all orderings of 1, 2, 3, 4, 5, 6, 7, 8. Okay. Where's the question? Yeah. So the next question is, suppose we throw two dice simultaneously, and an event is defined as the number of dots observed on the upper surface of both dice. So now what is your answer? What was the question? Sorry. Event is defined as number of dots observed on the upper surface of both dice. Yeah, so now your sample space would have like 36 elements. So this would be your answer. So like the number on both dice could be either 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, or it can be 2, 3, 2, 1, 2, 1, 2, 5, and so on. So that is the straightforward question. And now suppose a coin is tossed until a tail appears. So suppose the outcome of head is indicated by H. So now the sample space of this experiment, what is the sample space of the experiment? So we don't know when this head is going to occur. So we just keep tossing the coin till the head occurs. So let's say I toss the coin and the first tossing, I get tail. So in that case, sorry, what is happening? So yeah, in that case, it would be tail. And it could also be that in the first toss, I don't get a tail, I get head. And like, but in the second try, I get a tail. So I stop this turn. And it could also be the case that like I get head twice and then I get a tail. Or I can get head thrice and then get a tail. And then 4 times and then tail. So it could go on like this. So your answer to this question is, yeah, it's option C. So this would be your answer here. So a coin is tossed until a tail appears. So the sample space for this experiment would be this. The next question is, the complement of sample space, the complement of the sample space for the length of the useful life of a certain electronic component is a set of points T such that, so you have to like define this sample space like mathematically. So let's first understand the question. So let's just say, so this means that complement of sample space for the length of the useful life of a certain electronic component. So you can purchase an electronic component. So it could be a phone, or it could be a grinder, it could be a rice cooker, or it could be anything. So the life of this electronic could be 1 year, 2 months, 3 years, like it could be any positive number. So the sample space A would be any positive number, like 0, 1, 2, 3, 4, so anything. So what is the complement of A now? So it can't be 0. So yeah, if you want to have a good life, useful life, it has to be at least like one. It could like maybe just it could be 1 day or 1 month or 1 year. So it has to be 1. So this is A. So what is the complement of A now? The complement of sample space for length of U. So let's look at this. I can't scroll. Yeah. So each element here is T. So the T, this event T should be such that, so in the, like, how do you define A? So in the question, you have to define A complement. But first, let's see how to define A. So this A you would define as T such that T is greater than 0. So this is A. So what is the complement of A? T is such that T is lesser than 0. So lesser than 0 means it doesn't have a useful life. So that is the opposite of having a useful life. So I think the answer here would be T such that T is less than 1. So this option B is wrong because this is actually A. It is like the electronic having a useful life. It's not the complement of A. And T is equal to 0. This doesn't mean that the electronic has a useful life, like we just saw. It's not part of A either. So yeah. And this represents something that the electronics life could be anything between, let's say, maybe it could be 2 to 5 years. The 5 years. So this is, we cannot like define that this is a useful life. So if the electronic is good for 6 years, that is also a useful life. If the electron is good for 1 year, like some people might consider, oh, that is good enough. So you can't define the usefulness by an interval. So this is not the answer. So the correct answer for complement of the electronic having useful life is T such that T is less than 0. That's how you answer this type of questions. Oh, sorry. And now, yeah. So again, we come back to this medical experiment question. So 8 medicines numbered 1, 2, 3, 4, 5, 6, 7, 8 are given to 8 patients. So the sample space of the event is only that the even numbered medicines is effective. So here they're not saying anything about giving the even numbered medicine to the people. So it's just, they're just saying that the sample space is that the even number only will be useful, effective. So here it is your sample space would just be 2, 3, sorry, 2, 4, 6, and 8, which is option B. Yeah, so this answers this question here. Now again, so in a medical experiment, 8 medicines numbered 1 to 8 have given to 8 patients. So the sample space of complementary event that only even number medicines will be effective. So E was 2, 4, 6, 8. So this is even an event where the even number medicines are useful. But now they're asking complementary event to this. So the answer here is 1, 3, 5, and 7. So the answer is this. Option C is the answer here. Now let's say we throw 2 dice simultaneously. And an event is defined as the number of dots observed on the upper surface of both dice. And we define it as like all such points for which the sum is an even number. So like you have to consider all the points in both the dice together, and the sum has to be an even number. So what is the sample space now? So the sum can be an even number if 1 and 1 occurs, like 1 dot and 1 dot is 1 plus 1, 2. So it can be this, or it can be 1 comma 3, so which is 4. When you do 1 comma 2, it is 2 plus 1, 3. The sum is an odd number, so that is wrong. So 1 plus 3 is 4, so that is correct. And, or it can be 1 comma 5, which is 6. And then again 2 comma 2. And it could be 3 comma, it can be 3 comma 5, and so on. Like all such combinations where the sum is an even number is your answer. So that would be option D here. The option D. So 1 plus 1, 2, 1 plus 3, 4, 6, 4, 6, 6 plus 8. So yeah, all the even numbers with the sum is even number. So that is your answer. Now again, let's say we throw these 2 dice simultaneously and number of dots observed on upper surface of both the dice. So then which of the following represents the space of an event that the sum of the numbers on the upper face is a prime number? So yeah, you just have to know what are the prime numbers. 1, 3, 5. Yeah, so all these are prime numbers, 5, 7, and so on. So you just have to see that like what events would be that when you add these numbers, they are prime numbers. So the answer in this case is option D. Similar to the previous question. Now, this question, measurements of thickness of a copper connector might be modeled with the sample space as the set of positive real numbers. So let E1, event 1, so X is defined as X such that 10, X is like greater than or equal to 10 and less than 12. So E1 is 10 because there's an equal to here. So it's 10 and 11 and it's X is less than 12. It's not less than or equal to 12. So event 1 is just 10 and 11. And what is event 2? Event 2 is X of X such that like X is greater than 11 and less than 15. So that would be E2 is greater than 11, 12, 13, 14 and less than 15. So 15 is not here. So we have defined our two events, E1 and E2 now. So now we have to find E1 union E2. So what is the union here? You just combine everything. So there's nothing common between these two. But yeah, you just take 10, 11, 12, 13, 14. So X is greater than equal to 10 and X is less than 15. So you could define this by many ways. It could also be 11, like X is greater than 11, less than or equal to 14. Or it can be X is 11, less than 15. So what are, like, let's just look at the options, what we have. So this is wrong, no. So we have 10. So yeah, this is the correct answer. So here, by this definition of the option, we have 10, 11, 12, 13, and 14, which are all the elements here. But what is this? This is just 12, 13, and 14. Two elements are missing in this option, so this is wrong. So in this option, yeah, we just have X is less than 10. So which is like 0, 1, 2, 3 till 9. And X is lesser than equal to, we don't, so it's just like 11 and 12. So this is also wrong. We don't have any of these element in either of these sets, first of all. So this is also excluded. So this, by this option's definition, the values are 12, 13, and 14. So again, 10 and 11 are missing here. Like event 1 is missing. So the correct option is this option here. So where you have a E1 union E2. Now again the same question, but just like a different calculation. Like you have the same sets. So again, thickness of a copper connector might be modeled with the sample space, real positive numbers. Okay, we just have one set. We have E2 is equal to X is greater than 11, less than 15. So which means 12, 13, and 14. Now the complement of E2. Now what is the complement of E2 now? So complement of E2 is all the elements lesser than or equal to 12 and all the elements greater than 14. So you just have to see which of these options makes sense. So yeah, this option makes the most sense. So it has X 0 to 11. Sorry, it's not equal to 12. Yeah, complement. So we already have 12 here. So E complement will not have 12. It's just X less than 12 or X greater than 14. So yeah, you will have 0 to 11. And then you'll have, here you have greater than equal to 15, 15, 16, and so on. So you'll have all the positive numbers except 12, 13, 14. So this is your correct option. Now again, measurements of the thickness of a copper connector is the same story. So we define E1 is equal to x is greater x is greater than or equal to 10. So 10, 11, but it's less than 12. So there's no 12. And we have E2, which is greater than 11, less than 15. So just 12, 13, and 14. Now you have to do E1 intersection. I think the question is wrong here. Let me just check this. We Which question was it? I'm sorry. Question number 11. Yeah, let's look at this. So they've asked E1 intersection E2. But there's no common element between E1 and E2 here. Not sure. Okay. Yeah, the options are right. So now there's no common element between E1 and E2. You can see that. There's just these are mutually exclusive. So E1 has just 10 and 11. E2 has 12, 13, 14. So E1 intersection E2 is an empty set. So there's nothing. So let's see which of these options denotes an empty set. This is not empty. So it has 10, 11, 12, 13, and 14. Whereas this option, x is greater than 11, but x is less than 12. So there's no number between 11 and 12. There's no integer between 11 and 12. So this is an empty set. So yeah, so this is the answer to this question. Because E1 intersection E2 is an empty set. So this defines that. While the other options, they say like x is like 0 to 9 and then 11. By definition, option D is 12, 13, and 15. So none of these describe E1 intersection E2. So only this option describes it. So this is the answer. Empty set. Now again, here's just another. So here we define E1 is equal to 10, 11. So the complement of E1 is E1 complement, which can be all numbers less than 10 and all numbers greater than 11. So we have to find which of these functions describe that. So here, this one indicates 10, 11, 12, 13, 14. And this again describes an empty set. And here you have numbers 0, 1, 2 until 9, which is x is less than 10. And x is less than 12. And here you have wait, let me just. Oh. Just a minute. Where is my screen? Okay. Is this your assignment? Okay. Yeah, I'm sorry. Let's. So we have E1 is equal to 10 and 11. Complement of E1, what was it? So it's x less than 10, x greater than 11. Yeah, this we already saw. It's 10, 11 till 14. Here it's null set. So here you have numbers 0, 1, 2 till 9. Or x is greater than equal to 12. So this is OR. So mathematically you denote OR as like two pipes. So by OR you mean like, so this just means like the whole set would be 0, 1 till 9, and it will have 12, 13, 14, and so on. So this is equal to the condition we wanted. Numbers less than 10 and numbers greater than 11. So we have everything except 10 and 11. So that this best describes your comp E bar, E1 bar. So let's see what this is. So this describes 0, 1, 2 till 11, and all numbers greater than equal to 15. So 15, 16, 17, 18. So here it has 11. So this E1 also has 11. So E1 complement is not supposed to have 11. So this is not the answer. The correct option here is option C. Numbers 1 to 10 and all numbers greater than 11, which is like 12 and higher. This one. And question number. How many questions do you have? 16. We just saw question number 12. Now, question number 13. So here you have E1 is equal to 10, 11. Again, E2 is equal to 12, 13, and 14. Now, what is the question? You have to find E1 intersection E2. Sorry, E1 complement intersection E2. Now, what is E1 complement? E1 complement is 0 to 9 and 12, 13, 14, and all the numbers. And E2 is 12, 13, and 14. So what are the common elements between E1 complement and E2? So we have 12, 13, 14 here. We also have 12, 13, 14 here. So E1 intersection E2, E1 complement intersection E2 is equal to 12, 13, and 14. So how do we mathematically describe this? So here x is 10, 11, 12, 13, 14. It's not, this is null, no. This is also no, because this is like number 0 to 9 and then 12, like all the numbers greater than 12. And option D is x greater than equal to 12. So 12, 13, 14, less than 15. So option D is the correct answer here. It is E1 complement intersection E2. Now, coming to probabilities now. So random experiment can result in one of the outcomes A, B, C, D. So probability, sorry, yeah. So A has the probability of 0.2, B is 0.1, C is 0.4, and D is 0.3. So let A denote the event B and C. So A is equal to B and C. So now what is the probability of A? It is, what is, so it is 0.1 here and C plus 0.4. So probability of A is equal to 0.5. We have calculated that. Now we define B. B is an event A, B, D. So probability of B is 0.2 plus B plus 0.1 plus D is 0.3. So probability of B here is 0.6. 0.3 plus 0.1 plus 0.2 is equal to 0.6. So probability of B is 0.6. And probability of and then event C is equal to just C. So probability of C is equal to 0.4. So what are the options? Probability of A is 0.5, probability B 0.6. So yeah, this is the correct answer to your question. And now again, similar question. Where did I erase that? So A is 0.2, B is 0.1, C is 0.4, and D is 0.3. Now A denotes an event B, comma C. So probability of A is B plus C, 0.1 plus 0.4. So probability of A is 0.5. So we already, it's the same thing. So from the last question, if you remember, probability of B was 0.6, probability of C was 0.4. So now in this question, they've asked, what is A complement, B complement, and C complement respectively? So you just have to do, now probability of A complement is 1 minus probability of A is equal to 1 minus 0.5. So probability of A complement is also 0.5. And then probability of B complement is equal to 1 minus probability of B is 0.6. So probability of B complement is 0.4. And then probability of C complement is equal to 1 minus probability of C, which is 0.4. So 1 minus 0.4 is 0.6. So 0.5, 0.4, and 0.6. So this is the correct answer to this question. Probability of A complement is 0.5. Probability of B complement is 0.4 and probability of C complement is 0.6. Let me just edit this. Here we have these. Now the last question is a random experiment, the same thing. So outcomes A, B, C, D, probabilities 0.2, 0.1, 0.4, 0.3. A denote B and C. So we have already calculated the probability of A, probability of B, probability of C. And we also have the probability of A complement, B complement, and C complement. Now, we have to find probability of A intersection B, probability of A union B, and probability of B intersection C. So, yeah, like what is A again? A is equal to B comma C. B is equal to A, B, and D. C is equal to C. Now, what is A intersection B? What are the common elements between A and B? Only B is common. So A intersection B is probability of, like, it's just B is equal to, also what is the probability of this B? It is 0.1. So probability of A intersection B is 0.1. And then probability of A union B. So what are the common elements? Like combine A and B, what do you get? You get A, B, C, and D. You get everything. So when you add up all of these, what do you get? 7, 8, what? 4 plus 3, 7, 8, 9, 10. So you get 1. Probability of A union B is 1. And then B intersection C. So set B is A, B, and D. Set C is C. So there's nothing common between set B and set C. So it's an empty set. So probability of an empty set is 0. So which of these options have these values? Probability of A intersection B is 0.1, probability of A union B is 1, and probability of B intersection C is 0. So this option answers your question here. So yeah, these are just some examples of the theories we covered in week 2, which are set theory and probability. It's just like events and relative frequencies and like dice rolling. How do you define a sample space and event and all these? So these were just simple examples. And the assignment, which is due tomorrow, would also have similar questions. So that's all about today's class. I can share this with answers. Can somebody just confirm if you have access to the slides? Like, I know that the recordings are uploaded on YouTube. Like, in case you didn't know, the recordings are uploaded on YouTube. I could find them there.
Ma'am, I have one doubt, madam.
Yeah, sure. Who's speaking?
This is Vijayalakshmi, madam.
Yeah, just, yeah, sure. Go ahead. Please go ahead.
For one example, I read yesterday regarding a probability dice problem. A fair dice thrown for 2 times. A fair dice, DACE. DACE means plural or singular, I think. A fair dice thrown for 2 times. Then what is the sample space?
Okay. So it's just one dice is thrown 2 times.
No. Yeah, the question is a fair dice. I have a confusion in that word. A fair dice thrown for 2 times. Then what is the sample space?
What are the options? Can you share your screen maybe? I can have a look.
No, madam. No, options. Some of the options given, madam, but I need a clarification. That die means outcome, 6 outcomes. A fair dice, what is the meaning of fair dice? I don't know, madam. A fair die.
Singular.
FAIR. DAE. Yeah. Mm. I don't have an idea of fair dice.
Fair dice. Usually dice also refers singular.
Yeah.
Otherwise, you usually in your question you would have something like this. Let us see. Like if they are referring to 2 dice, they usually say 2 dice. So you throw two dice
Two
simultaneously.
dice? Yeah.
Yeah.
Madam.
So a fair dice or a fair, just give me a fair dice and fair die. All of these represent just one dice. One dice. So when they say two dice simultaneously, it means two dice. So this question, a fair dice is thrown twice. So you just throw the dice twice. So the sample space when you throw the dice once could be 1, 2, 3, 4, 5, or 6. Is that the question? Like, is that all? Like, uh, so I think the answer would be, so even in this case, a dice is thrown twice. So you have two observations. Like your end outcome is two observations, right? It doesn't matter. Like if you throw two dice simultaneously, you'll have two observations, which was denoted by 1, 1, 1, 2, and so on, right? So even in this case, it's similar to that. So one dice is thrown twice. It still means that your outcome is you have two values. So when you throw one dice once, you get one. You throw the dice again, you get two or something. So it's still the same as this. So even in this case, your sample space would be all those 36 elements. So you would have 1, 1, because the single dice you throw two times. First time when you throw the dice, it could be 1. Second time you throw it, it can be any other number. So yeah, even in this case, your sample space is all these 36 elements.
So this is also similar to two dice thrown.
Yes. So you have to just look at the outcome. So whether you throw two dice, your final outcome is two values. You throw one dice twice, your outcome is again two values. So yes, it's similar
Thank
to
you,
throwing
madam.
dice twice. Yeah.
Thank you. Thank you.
Don't I erase this? Yeah. Yeah, if anybody has any other questions related to this. Yeah, if you had any questions related to these problems or any concept, yeah, please let me know. Not if I erase this. Yeah, maybe it's just, yeah, that's all from my end. Dr. Purna's hands are raised. Did you have any question? No. Yeah, if no more questions, yeah, we could end the class. Thank you. Thank you for attending.